Hello and welcome to this new video where we discuss mathematics and physics on the board. Today I've got actually just the context that is written quite already, and then we're going to see an example. So what we are going to see today is basically discussing what is called the Buckingham 𝝅-theorem, and basically how it can be used in a simple problem. And then in future videos we are going to see how this can be used in more complicated problems like fluid dynamics, for example. Right, okay, so let's set a little bit of the context. The 𝝅-theorem, or the Buckingham 𝝅-theorem, has to do actually with physics or any kind of discipline of the quantitative sciences that also involves dimensions. And what I mean by dimension here is a sort of meaning that we attach to a quantity. So for example, if I have, like in economics, if I have a dollar, I've got a dollar, but in principle I can't necessarily add up a dollar with an apple, for example, or a dollar with an emotion or something like this. And essentially what that means is that a dollar has a particular dimension, which is, let's say, a currency, and then an apple is basically a fruit, right? That is kind of what it is. And so I can't necessarily add up a currency and a fruit. And so what people do in economics, for example, is that they need to convert, so to assign a price to an apple, and then they can add up that to dollars if they want to. But basically there's a sort of conversion that needs to be done, because otherwise these concepts are radically different. And so what that means is that they've got different dimensions. Now in physics, we basically always deal with dimensional quantities. So these are quantities that have a sort of meaning in the physical world that corresponds to ways of doing measurements with regards to some, let's say, elementary property. And I'm going to narrow this down to a different term in a few minutes. Formally speaking, the point here is that in physics, quantities have dimensions. And of course, I don't mean dimensions in the technological sense, where you're going to give the dimensions of a cube, for example. So simply the length the length, width, and height of a cube. So that's not the kind of dimension I'm talking about. I'm not talking about the dimension of a linear space, or even a topological space, or anything like that. This is, in a sense, basically a dimension in a space of concepts. And I think that's how you could view it. It's a dimension, intercept, or in the space of concepts, relating to how many concepts you need to describe that particular quantity. So dimensions, so quantities are dimensions, and these dimensions are categorized according to the dimension. So we need to somehow have the same notion as that of a basis that you would have, let's say, in linear algebra and so on, of primitive concepts. So you need to come up with a notion of primitive concepts that have no other dependency on anything else, conceptually speaking. Usually these primitive concepts cannot be kind of defined very, very precisely. You need at some point to say, I'm going to define this as being a length, and then you don't go into any of the details about how you go about defining length, because at some point you run into circularity. So essentially, primitive concepts serve as axioms of your physical theory. You admit that there is a notion of length. You admit that there is a notion of time interval that is measurable with whatever standards you use for time, and you then also admit that there is a primitive concept of mass, and so on and so forth, with electric charge, etc., etc. So this is what these primitive concepts are. They are necessitated, let's say, by the circumstances when you want to describe phenomena. They are incorporated usually in our language, and so usually we can't in fact define them, because there is nothing else to define them with respect to. And basically, we use that then as a basis to define everything else. So any physics equation is going therefore to involve quantities that are either primitive directly or derived from this primitive concept. Descartes, for example, thought that everything was just a combination of length, of let's say of distances and time intervals. And that's only when it comes to perhaps Galileo and Newton, more particularly, that then we get these notions of mass, and where the mass really enters into the picture and in the physics as well. Now, derived quantities, therefore, have dimensions that is resulting and only resulting from the product or quotient of primitive dimensions. Okay, so that's the only way to form a new dimension from a previous one is essentially product and quotient. And what that means is that essentially you can't create a new dimension by adding dimensions, for example. That's forbidden. So the only possibility is to take again the product or the quotient. So for example, here I just put length and time interval. If you take the quotient of length of a time interval, you basically get the dimension of velocity. If you then take, let's say, mass, the quotient of, the product of the mass product with mass times length, so mass times length, and then divided by time interval twice, is going to give you a force, and so on and so forth. Okay, so that's kind of how it works. And so it's just again to set the stage in terms of dimensional analysis. And finally, dimensional analysis could not be done if we didn't have this particular requirement here, that in physics, we require our equations to be so-called dimensionally complete. So what that means is that you can only add up or equate, so you can only add quantities or equate quantities that have the same dimension. And that's a huge requirement, okay? There are plenty of quantities that exist in engineering that have been measured and where essentially they only work in certain units, and when you check, they are not dimensionally complete. So that basically there's just, for example, a fudge number that is there, and then you can't work out how it would work in any possible, for example, unit system. In that case, it's not a complete equation. So here the bottom line is that in physics we require that, and that really emphasizes the fact that in physics what we are looking for are relationships between quantities. We are rarely looking for actual numbers. That would be the job of the engineers and the chemists sometimes as well. But for most of the time, what we care about is relationships between variables. And so that's going to come from there. Now, if you actually take this particular statement seriously, you can think a little bit. So I'm just going to state it here because, to be honest, it does not necessarily require much proof. But a consequence of this requirement is that if you have a physical system that is characterized by m independent variables, so whatever, we are going to give an example in a few seconds, m independent variables involving n different dimensions, then you can reformulate whatever number of equations you had for your physical problem, you can reformulate them in terms of simply m minus n, dimensionless variables. Dimensionless variables mean essentially that the dimension, when you calculate it, is 1. And so what that means is that if you've got a sort of algebra of the dimensions, and all of these guys have power 0. So dimension 1 or dimensionless means that if you express the dimension of the quantity, it can't be expressed, it's a length to the power 0 times to the power 0 and so on. So all of these guys have power 0 there. So let's actually give an example about how that works. So imagine that's a very typical example, by the way. So that you've got a simple pendulum. Okay, so you've got a simple pendulum, so this is going to look like this. And I'm going to say that your pendulum starts with some initial kind of angle, which is theta 0. And then here there is a weight acting on this. So this is y, and this is x. And then in principle, I should not forget that if I put this in principle, I need also to put this here. So there is a tension from the wire there. And let's say physically, I'm observing when I do the experiments that actually there is a period that occurs, a period of oscillation of that stuff. Okay, there are various ways theoretically as well to predict that there must be an actual period, but for the time being, I'm just going to focus on the fact that there is a period. Okay, so the physical quantities that I'm going to have, if I'm just naively listing these quantities, I'm going to have that I must express that as a function. So I'm going to say that the equation I'm interested in here is basically has to be a function of tau, that's the period, then let's say the mass, the acceleration of the weight on Earth, then we've got, I forgot the length, L, of the wire or the rod, so tau mgl, and then I've got theta 0, and in principle I've got the magnitude of the tension, and this, you know, could be said to be 0. So let's say you say that the equation that is satisfied by all of these variables is 0, and again the uppercase T here is a tension in the rod, and the tau here is a period you're looking for. Now, if I apply 𝝅-theorem, so here I've got 6 variables, so m is equal to 6, and n here is equal to what? Well, if I check, I've got m, which is here in kilograms, so that's a mass, so I've got 1. Then I've got tau here, which is a period, so that's a time, so that's 1. And then here, by the way, this is, when I say the number of different dimensions, this is a number of different primitive dimensions that are involved, because again, everything else can be recovered by the product and quotient of these guys. Okay, so let me put it just clearly here. So different primitive dimension, primitive or elementary dimensions that you can look at. And then n here is equal, so I said mass, time, and then I've got length here. So that's actually 3, because we take the convention that angles don't have dimension. That's a very interesting topic actually that I will discuss in another video, but not today. So but that's basically where we are. So now I need to check how can I combine things together so that I get dimensionless quantity. So it means that I can reformulate that as being a function, and let's put the things that are dimensionless. So here theta 0 I know is dimensionless, so I've got theta 0 here, and then I need to construct, let's say, how do I form something that is dimensionless with the mass, for example? Well, it's not that straightforward, but the way I can do that is I know that if I multiply m times g, and then I divide by t, I actually get something that is dimensionless. So m times g over t is dimensionless, and then I need to find how do I express this tau here. So again, there are multiple ways this can be done, but I need to combine it with something to actually get something that is dimensionless, that has only the dimension of time. So if you actually look at these numbers, tau as dimension of time, g as dimension here, what is called L and then t minus 2, so time minus 2. I should put different things for time. So let's say this is L and then t minus 2. So what I see is that if I actually put this, if I divide g by L, I've got 1 over t minus 2. So if I take the square root, I've got 1 over t. So I can say that this is tau and then square root of g over L. That's going to be dimensionless. And basically here I've actually reached my limit because it's m minus n independent dimensionless variables, and so it means that there is a function where I can write this. Okay, now the trick here is that, as I said, I naively kind of set the variables as being like this. Now one of the tricks is that the actual tension in the rod is not actually independent from the weight. So here what was important is that you've got a physical system with m independent variables that you can kind of set experimentally, if you will, independently of each other. But that's not the case. You can't set the actual tension in the rod independently of the mass of the object. Okay, it's actually completely dependent on it. So what that means is that actually t and m and g, basically this guy, does not enter in our description of the problem because t and mg are actually not independent. Now you could have said, well, I can just remove t here and keep the m, for example. But if you do that, then you're going to realize that you are not able to create any quantity with m that is going to be dimensionless. And so you need to get rid of t and m kind of all together. Okay, so that's kind of the important part here. So that's kind of how it works. And so now we are left with this expression. And then you can say, well, let's kind of invert that expression and express this in terms of tau is equal to something. So then you want to convert that into tau is equal to, and then you need to find out what it can be. Well, what we know is that the only quantity that has a dimension of time, now that we've gotten rid of this, so this had the dimension, this was dimensionless anyway, but the only quantity that has a dimension of time is 1 over that. Okay, and that's it, nothing else. So what I can say is that this is equal to some constant here. I don't know what that constant is, but I know that it's independent of t0, of theta 0. I know that it's independent of g and L. So I've got some constant here. Then I've got square root of L over g. And then I have some function that I'm going to call, not sure how to call that, to be honest. Let's say h of theta 0. Okay, so that's a general formula you can infer for these kind of things. Okay, and the thing to at that point, you can't necessarily go further. You need to actually do some calculation or some presupposition. One of them is to claim that if basically that h of 0 is equal to 1, and so in that case, for small angles, you're going to get that this is proportional to the ratio of L over G, which is a traditional period of the pendulum that people learn in secondary and high school. Okay, so that's kind of the idea. You can just say for small oscillations, so assume that h of theta 0 is approximately 1 if theta 0 is much smaller than 1, and then we get the traditional formula that tau is equal to some constant, and this constant is actually just 2 pi L over G and then square root. Okay, which is a traditional formula you get. But notice here that when I derive all of that, I didn't need to use any kind of physics, right? Apart from the dimensions. I didn't need to use any Newtonian mechanics or anything like that, apart from I set up kind of the problem and I try to distinguish which quantities depend on which. But apart from that, I didn't have to solve any equation. Okay, so that's kind of the power of this Buckingham 𝝅-theorem. So basically that's it for today. If you've got any questions or comments, by all means, do let me know in the comment section, and otherwise see you in the next video.